Welcome to Part 2. Route Tables and Infrastructure. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. In Part 1, we built a complete mental model of Azure service chaining with gateway transit. You saw how traffic flows through the architecture. Now in Part 2, we're rolling up our sleeves to implement the foundation, creating VNets, subnets, and most importantly, the route tables that control traffic flow. Route tables are the heart of service chaining. They're what override Azure's default routing behavior and force traffic through your security appliances. Get them wrong, and traffic either bypasses security or gets blackholed. Get them right, and you have enterprise-grade traffic control. I'll show you exactly how to create each component, explain every parameter in detail, and visualize what happens at each step. We'll start with the hub VNet and its specialized subnets, then create the spoke VNets, and finally implement the route tables that tie everything together. By the end of this video, you'll have the complete infrastructure ready for NVIDIA deployment and gateway transit configuration. Every command is production ready, and I'll share the lessons learned from dozens of enterprise deployments. Let's start by creating our hub VNet, the foundation of our entire architecture. The hub VNet is the cornerstone of our architecture. Everything connects through it, so we need to get it right from the start. Let me walk you through creating it with the exact specifications needed for service chaining. First, we create the resource group. I always use a dedicated resource group for core networking components, as it makes management and RBAC much easier. The location is critical. You'll want to choose the region closest to your users or where you have the most resources. Everything we create must be in the same region. For the VNet creation, notice the address space of 10.1.0.0/16. This gives us a large number of IP addresses to work with, which is plenty for all our hub components. I've chosen 10.1.0.0/16 deliberately to avoid conflicts with common on-premises ranges like RFC 1918. The hub needs 4 specialized subnets, each serving a specific purpose. The gateway subnet at 10.1.1.0/24 must be named Gateway Subnet. Azure looks for this exact name. No route tables can be associated with it. Azure manages its routing automatically. The /24 size gives us 256 addresses, supporting multiple gateways if needed. The firewall subnet at 10.1.2.0/24 will host our first NVA. The /24 size allows for multiple firewall instances for high availability. The IDS subnet at 10.1.3.0/24 hosts our second NVA in the chain. Again, a /24 provides room for growth. The management subnet at 10.1.4.0/24 is for jump boxes, monitoring tools, and administrative access. It typically has different routing rules, often bypassing the service chain for management efficiency. Notice how I'm creating all subnets immediately. This prevents someone from later creating a subnet that conflicts with our planned IP ranges. It's a defensive practice I learned the hard way. Creating spoke VNets. Now let's create the spoke VNets. These represent your actual environments, for example, development, testing, and production. Each spoke is isolated by default, which is exactly what we want for security. I'm using a clear naming convention: Spoke 1 VNet, Spoke 2 VNet, and Spoke 3 VNet. In production, you might use names like Dev VNet, Test VNet, or Prod VNet. The key is consistency. It makes automation and troubleshooting much easier. For address spaces, I'm using 10.2.0.0/16, 10.3.0.0/16, and 10.4.0.0/16. Each spoke gets a full /16, providing plenty of room for growth. The sequential numbering makes it easy to remember which spoke is which. Some organizations prefer non-contiguous ranges for security through obscurity, but I find the operational simplicity of sequential numbering more valuable. Each spoke starts with a default subnet using a /24 from their address space. This is where your workload virtual machines will live. Notice I'm not creating multiple subnets initially. You can add application-specific subnets later as needed. Starting simple reduces complexity. The diagram shows how these spokes are isolated islands at this point. They can't communicate with each other or the hub. This isolation is a security feature. We'll explicitly enable communication through peering and route tables, ensuring all traffic flows through our security controls. One important note: resist the temptation to create large, flat networks. Each spoke should represent a security boundary, perhaps an environment like dev, test, or prod, or an application tier. This segmentation is crucial for limiting blast radius in security incidents. At this stage, virtual machines in these spokes can only communicate within their own VNet. They can't reach the hub, other spokes, or the internet. We'll fix that with route tables, but this default isolation is a security benefit. This is where the magic begins. The spoke route table is what forces all traffic from spoke virtual machines through our service chain. Let me explain every parameter and design decision. The route table name, RT spoke to hub, clearly indicates its purpose. In environments with many route tables, clear naming is crucial. I've seen environments with names like RT1 or RT2, which are impossible to troubleshoot. The critical parameter is disable BGP route propagation set to false. This allows BGP routes from the VPN gateway to propagate to this route table. If you set this to true, spoke virtual machines won't learn about on-premises networks through gateway transit. It's a common mistake that breaks hybrid connectivity. Now for the route itself. The address prefix, quad 0/0, is a default route. It matches any traffic that doesn't have a more specific route. Think of it as a catch-all. Without this, Azure would use its system default route, which would bypass our security controls. The next hop-type virtual appliance tells Azure to forward traffic to an NVA instead of using standard routing. The next hop IP address, 10.1.2.4, is the firewall's IP. This must be a static IP because if your firewall's IP changes, routing breaks immediately. The diagram shows the effect. All traffic from spoke subnets, except local VNet traffic, now routes to the firewall. This includes internet traffic, inter-spoke traffic, and on-premises traffic. The firewall becomes the central control point. One subtle but important point: this route table can be shared across all spoke subnets. Since they all need the same routing behavior, with everything going to the firewall, one route table serves all spokes. This simplifies management and ensures consistency. Creating the firewall route table. The firewall's route table is more complex because it needs to make intelligent routing decisions based on destination. Let me walk through each route and explain the logic. First, notice we keep BGP propagation enabled. False means enabled, which is confusing, I know. The firewall might need to know about dynamically learned routes from on-premises to make routing decisions. Some security appliances use this information for policy decisions. The first route sends all private IP traffic for 10.0.0.0/8 to the IDS/IPS at 10.1.3.4. Why/8 instead of specific /16s? This single rule covers all our networks, including the hub at 10.1.0.0/16, the spokes which use the 10.2, 10.3, and 10.4.0.0/16 networks, and the on-premises network at 10.0.0.0/16. It's simpler than creating multiple specific routes and accommodates future growth. The second route for 192.168.0.0/16 handles our second on-premises range. You might wonder why we need this when we will add a quad 0/0 route. The reason is precedence, as more specific routes take priority. This ensures on-premises traffic goes to the IDS, not directly to the Internet. The default route, quad 0/0, also goes to the IDS. This catches all Internet-bound traffic. The firewall's job at this stage is policy enforcement, which involves checking if the source is allowed to reach the destination. The actual Internet egress happens later in the chain. The diagram shows how the firewall is now a routing decision point. It receives traffic from spokes and forwards everything to the IDS for deep inspection. This two-stage approach, using the firewall for policy and the IDS for inspection, is a defense in-depth strategy. Notice we haven't associated this route table yet. We're just defining the routes. Association comes later, after all route tables are ready. This prevents partial configurations that could disrupt traffic. The IDS/IPS route table is the most complex because it makes the final routing decision for each traffic type. This is where traffic gets sent to its actual destination after inspection. First, notice the parameter disable BGP route propagation is set to true. We're explicitly managing every route from this point. We don't want BGP routes potentially overriding our security controls. This gives us complete control over traffic flow. For each spoke, we create a route with the next hop type VNet local. This means use Azure's native VNet routing. Since the hub is paired with all spokes, VNet local routing can reach them. This is more efficient than routing through another appliance. The routes to on-premises for the RFC 1918 address spaces use the next hop type virtual network gateway. This sends traffic to the VPN gateway for transmission to on-premises. Note that we don't specify an IP address for the virtual network gateway. Azure knows where the gateway is. The default route, quad 0/0, is interesting. It points back to the firewall's external interface, 10.1.2.10, for Internet egress. Why? Because the firewall performs NAT for Internet traffic. The IDS inspects the traffic, but the firewall handles the actual Internet connection. This creates a logical flow. From the spoke, to the firewall for policy, to the IDS for inspection, to the firewall for NAT, and then out to the Internet. Return traffic follows the reverse path. It seems complex but provides defense in depth. The diagram shows how the IDS becomes the final routing decision point. After inspection, it sends traffic to the appropriate destination, spokes via peering, on-premises via the gateway, or the Internet via firewall NAT. The management subnet often needs different routing than production traffic. Let me explain this design pattern and when to use it. For the management route table, we typically allow direct Internet access by setting the next hop type to Internet. This bypasses the service chain, which seems like a security risk. However, it's a calculated trade-off for operational efficiency. So, why bypass security for management? First, management tools often need to download updates, packages, and patches from the Internet. Routing this through your security stack can cause issues, as some security appliances block or throttle large downloads. Second, if your security appliances fail, you need a path to reach management tools for recovery. The specific routes for RFC 1918 ensure management traffic to internal networks still goes through security. We only bypass security for Internet traffic. This allows administrators to reach internal resources while maintaining security inspection for lateral movement. This pattern is controversial. Some organizations mandate all traffic goes through security, including management. Others recognize the operational benefits of direct Internet access for management. There's no universal right answer. It depends on your security posture and operational needs. If you do implement this pattern, you must compensate with additional controls. Use just-in-time access for management virtual machines. Implement strict NSG rules. Enable Azure Bastion for secure RDP/SSH, and monitor management subnet traffic closely. The diagram shows how management traffic takes a different path than production traffic. This split routing approach is common in enterprise environments where operational efficiency and security must be balanced. Associating route tables to subnets. Now comes the critical step. Associating route tables with subnets. This is where our routing rules actually take effect. The order and timing of these associations matter greatly. We start by associating the spoke route table with all spoke subnets. The AZ network VNet subnet update command modifies an existing subnet to use a route table. This association takes effect immediately, and existing connections might be disrupted as routing changes. For production environments, I recommend associating route tables during maintenance windows. I've seen cases where route table association broke active connections, causing application errors. Plan accordingly. Notice we're using the same route table, RT spoke to hub, for all spoke subnets. This is a best practice, as spokes with identical routing needs should share route tables. It reduces management overhead and ensures consistency. For the hub subnets, we haven't associated route tables yet. Why? Because we haven't deployed the NBAs. If we associated the firewall route table now, it would try to route traffic to 10.1.3.4, the IDS IP, which doesn't exist yet. Traffic would be blackholed. This is a crucial lesson. Only associate route tables when the next hop IPs are reachable. Otherwise, you create a routing black hole. In Part 3, after deploying NBAs, we'll associate the hub route tables. The diagram shows the current state. Spoke traffic is being routed to the firewall IP, but since no firewall exists yet, traffic fails. This is expected. We're building the foundation before adding the components. Also note, you can't associate route tables with the gateway subnet. Azure manages gateway routing automatically. Attempting this association will fail with an error. Before moving forward, let's verify our route table configuration. These verification steps will save you hours of troubleshooting later. I'll show you exactly what to check and what the output means. The first command lists all route tables in your resource group. Verify that all 5 route tables exist with the correct names. The output table shows location, provisioning state, and resource group. All should show succeeded for provisioning state. Next, we examine the routes within a specific route table. This JSON output shows all routes and their properties. Check that address prefixes and next hop IPs match your design. A common mistake is typos in IP addresses. For example, 10.1.2.40 instead of 10.1.2.4. The subnet show command reveals which route table is associated with a subnet. The route table property in the output shows the full resource ID of the associated route table. If this is null, no route table is associated, and Azure uses system default routes. For spoke subnets, you should see RT spoke to hub associated. For hub subnets, they should still be null at this stage since we haven't deployed NBAs yet. This is the expected state. These verification steps become muscle memory with practice. I run them after every change to ensure the configuration matches my intention. It's much easier to catch errors now than during a production outage. The diagram summarizes what we've built so far. A hub and spoke topology with route tables defined but not fully implemented. Spoke traffic is directed to a firewall that doesn't exist yet. In Part 3, we'll deploy the NBAs to complete the chain. We've accomplished a lot in Part 2. The foundation of our service chaining architecture is now in place. Let me recap what we've built and preview what's coming next. We created the hub VNet with 4 specialized subnets, each serving a specific purpose. The gateway subnet for our future VPN gateway, firewall and IDS subnets for our security appliances, and a management subnet for administrative access. We built 3 spoke VNets representing different environments or security zones. These are currently isolated islands. They can't communicate with each other or the outside world. Most importantly, we created 5 route tables with specific routing rules. The spoke route table forces all traffic to the firewall. The firewall route table forwards to the IDS. The IDS route table makes final routing decisions. The management route table provides operational flexibility. We associated route tables with spoke subnets but not the hub subnets. We need NVAs deployed first to avoid black holes. This staged approach prevents disruption. In Part 3, we'll deploy the network virtual appliances and complete the service chain. You'll learn how to configure NVAs for routing, enable IP forwarding, and implement high availability. We'll also establish VNet peering to connect our spokes to the hub. Part 4 will add gateway transit and VPN configuration for hybrid connectivity. Part 5 covers monitoring, troubleshooting, and optimization techniques. The foundation is solid. Next time, we'll build upon it to create a functioning service chain. Thank you for your attendance. Please consider subscribing to the channel.